Hi there, and welcome to the test review. If I were you, I would try the whole thing by myself first and then use this just to check the problems you're still confused about. Or if you want, you can watch the whole thing while you're working on the test review. So first of all, true or false? A translation represents an isometry. An isometry is a transformation where your pre-image and your image, so like maybe that's the first shape and that's the second shape, we want them to be exactly the same size or congruent. In a translation, that's true. I'm just sliding it over. In a reflection, I'm just flipping it over a line of symmetry, so my original and my new shape are the same size. In a dilation, though, one of them's little, one of them's big, so that is not an isometry. And last one, a rotation. Yeah, I'm just turning it, so I'm not changing its size. That one is an isometry. Let's make my pen a little bit smaller here. Next question. Below are two hexagons in which a transformation has been applied. The transformation changed the orientation. In other words, the image has reversed orientation from the pre-image. So label the image. When I look at the first one, it appears that A, B, C, D, E, and F are all labeled going counterclockwise. So to reverse the orientation, I'm just going to go the other way around. So instead of counterclockwise, I'm going to label clockwise. So this would be my B prime, C prime, D prime, E prime, and F prime, the opposite way of the original. Alright, so some reflections. I've got this original shape and I'm reflecting over the y-axis. Let's make my line of symmetry maybe a different color. So, whoa, got a little off track there. Ooh. Let's see. So my line of symmetry right here, the y-axis. Now let's go back and I'm going to count how far it is from like point C, 1, 2 spaces to the line of reflection, 1, 2 spaces on the other side, that's my C prime. B is 1, 2, 3, 4, 5, 6 spaces. So I'd go 1, 2, 3, 4, 5, 6 spaces over here. There's B prime. A is 1, 2, 3 spaces away from the line of symmetry. 1, 2, 3 spaces on the other side. There's my A prime, and I'm done. And I labeled my picture. It's oh so pretty. My most favorite shape, the triangle. And now I'm moving on to the next one. So I'm not reflecting over an x or y axis, I'm reflecting over a line. Y equals -2. Let's think for a minute about what that line might look like. We've got our fun little saying, Buck's boy, which says that horizontal lines have a zero slope and are y equals. So this is going to be a horizontal line where the y value is -2. That happens, I go to my y-axis, -2 is like right there. And in fact, any of these dots have y values of -2. So I'm going to draw in a line of symmetry to reflect over. There it is. Get my pen back out. And point A is right there on the line of symmetry. So A prime is going to be that exact same point. It doesn't move. B, though, is 1, 2, 3 spaces away, so I want to go 1, 2, 3 on the other side. There's B prime. Point C is 1, 2, 3 spaces away, so I want to go 1, 2, 3, 4, wait, sorry, C is 1, 2, 3, 4, 5, 6 spaces away, so I'll go 1, 2, 3, 4, 5, 6 on the other side. There's C prime. And connect the dots to make a beautiful triangle. Kind of looks like a little Pac-Man sort of guy there. Ooh, here's where it gets harder. So in this one, I'm reflecting over y equals x. That's not a horizontal or vertical line. That's our diagonal line, the one that starts at the origin and has a slope of 1. So over 1, up 1, over 1, up 1, over 1, up 1. A lot of times it'll just kind of go through the corners of my box here. So I'll draw that guy in. This is a little bit harder to do the reflection for. So I'll show you kind of two ways to do it. One is just by counting instead of counting like along the sides of our boxes, we're going to count diagonally. So like point B is 1, 2, and a little bit diagonally to that line of symmetry. So I'd go a little bit, 1, 2 on the other side, and there's my B prime. The other way you could do it, the original point B is at 1, 2, 3, 4, 5, 6, 6, 1. And you'll notice that B prime ended up being at 1, 6. So a quick way to get your coordinates when you're flipping over the line y equals x is just to switch x and y. So that could be a quick way to get your points. I'm going to go on counting though. So point A is 1, 2, and a little bit away from the line of symmetry. So I'd go a little bit, 1, 2. There'd be my point A. Again, you could get it just by switching the x and y coordinates. And last one, point C is, let's see, it's hard because my line's kind of off a little bit. Point C is just like one diagonal space away from the line of symmetry, so I'm going to go one diagonal space. It's kind of on the inside of the original shape. And there is my new shape, the reflection. For number 6, I'm reflecting over the line y equals 1. And I already drew the line of symmetry in a little bit earlier. Whoa! For this one. There it is. So there's my original graph. X equals 1. Sorry, I said y equals 1. X equals 1. Vertical lines have an undefined slope and are x equals. So a vertical line that goes through an x value of 1 would be everything along those dotted lines. So I'm going to go put my line of symmetry back. And then I'll start counting. So point C is, whoa. Point C is 1 space away from my line of symmetry, so I'm just going to go 1 on the other side. That's C prime. B is 1, 2, 3, 4, 5 spaces away, so I want to go 1, 2, 3, 4, 5 on the other side. A is 1, 2 away, so I want to go 1, 2 on the other side, and then label them, B prime, A prime, and connect my dots. Oh, so marvelous. Almost done with the reflections. We've got the ordered pair 3, negative 2, and we're reflecting over y equals x. You can do this by applying a rule, or you could test it out in the coordinate plane. So like point 3, negative 2 is right there. Ooh, so we've done this one before. Cool. When I flip it over the line y equals x, so I count 1, 2, and a little bit, 1, 2. What I noticed was that my answer was up at negative 2, 3. So I just switch my x and y. When I'm reflecting over y equals negative x, though, that's the line that's going the other way. So it starts at the origin, but it's going down from left to right. So let's draw that guy in really quick. So it starts at the origin, has a slope of negative 1. So I'm reflecting over that line. The point that I'm trying to reflect right here at 3, negative 2 is just a little bit away from the line of symmetry, so I'm going to go a little bit on the other side. And that puts me at 2, negative 3. So I could get it from the drawing, or maybe the quick way to get there, the original point was at 3, negative 2. The new point was at 2, negative 3. So I had to switch the numbers, put the 2 first, 3 last, and change their signs. So that's like a rule if you want to remember it that way. Alrighty. So we're done with reflections now, and we're moved on to translations. So I want to give a vector that describes the translation. When I look at this picture, it's important to recognize which of these is the new and which of these is the old. When I see these little prime markings, that shows me that this shape over here on the left is the new, sorry, new, not mu, and then this one over here on the right is the old. I'm just going to pick 2 points that are corresponding to each other, like A and A prime, and see how I get from one to the other. So to get from A to A prime, first of all, I'm going left, 1, 2, 3, 4, 5, 6. So if I'm going to the left 6, that's a negative 6. And then from there, I'm going down 1, 2. Down is also indicated with a negative. So this vector is one way that you could write the rule. The other format that we've seen in class is where you've got x, y being mapped to x minus 6, y minus 2. So that could be the other way that you write your answer down. All right, next one, I'm being given the point 3, negative 2, 6, 1, and 2, 4, and I'm supposed to translate them using this vector. So let's graph those. So 3, negative 2, 6, 1, and 2, 4. Okay. So I'm going to do my old one in black, and now I'm going to graph the new in blue. So I'm going to take each of my points, and I'm going to, according to that negative 2, I'm going to go left 2. According to that 1, I'm going to go up 1 space. So from point A to the left 2, up 1. There's my new A. From point C to the left 2, up 1. There's my new C. And B to the left 2, up 1. There's the new B. Connect my dots. The other way to get those answers, which we'll see in the next example, is just by adding whatever numbers are in the vector to each of your points. So actually, hang on, let's see. Describe the translation of the point A to the point A prime using vector notation. All right, so this is the old one. It doesn't have the prime marks. This is the new one. And I just have to think about how am I going to get from the old to the new. So if I'm starting at an x value of 3 and then ending at an x value of negative 1, I've got to think about how did I get there. Oop, this is a vector, not an ordered pair. So to get from 3 to negative 1, I've got to subtract 4. To get from negative 2 to 5, I've got to add 7. So that is my vector. Types of symmetry. Which of the following does not have point symmetry? Point symmetry is the one where you could turn it 180 degrees or upside down and it would look the same. So like if I turn Z upside down, it still looks like a Z. If I turn I upside down, it still looks like an I. Turning N upside down still looks like an N, but if I turn M upside down, it looks like W. So that one does not have point symmetry. Next one, I'm figuring out how many lines of symmetry each of the following has. And I'm going to draw the lines of symmetry and then give a rule about how the number of lines of symmetry relates to regular polygons. Regular polygons, remember, are the ones that have sides and angles that are all congruent. So with my triangle, I could divide it in half 1, 2, 3 ways, which is kind of cool because a triangle has 3 sides. A square has 1, 2, 3, 4 lines of symmetry. Again, kind of cool because it had 4 sides. A pentagon, 1, 2, 3, 4, and 5. 1 through each of the vertices and the side opposite. So 5 lines of symmetry. And just by kind of recognizing this pattern, I'm betting the hexagon is going to have 6 lines of symmetry. But we got to draw them in as part of the problem, so let's do that. We've got lines through each of the opposite sides. Ooh, that last one was yucky. And then also through each of the opposite vertices, or those little intersection points. 1, 2, 3 more. 6 lines of symmetry. The pattern that you're seeing is that the number of sides that a shape has, if it's a regular polygon, is equal to the number of lines of symmetry. Alrighty. Which of the following has rotational symmetry? So that means I could turn it some amount less than 180 degrees and I'd get a shape that looked exactly the same. With a heart, I've got to turn it all the way around 360 to make it look like a heart again. That doesn't count. A rotation has to be, or rotational symmetry has to be less than 180. So that one does not have rotational symmetry. This one, I could turn it just 90 degrees and it would look exactly the same. So that one is a yes. That one, I'd have to turn it all the way around to make it look the same, so it's a no. Same thing here. I'd have to turn it all the way 360 to make it look the same, so not rotational symmetry. Last ones for the page. Which of the following does not have line symmetry? Let's start drawing some lines. That one, I could divide in half. That one, I could divide in half. That one, I could divide in half. But this is kind of an irregular shape. There's no way for me to divide it exactly in half. So that's the one that does not have line symmetry. So moving on to another transformation, dilations, making stuff bigger or smaller. Let's plot our original points. 1, 2, 2, 2, -1, 1, A, B, and C. And I'm going to create a dilation that has a scale factor of 3. So a scale factor of 3 is going to end up giving me an enlargement. Something bigger than 1 makes a larger shape. I think the easiest way to get the new points would just be to, right up here above, I'm going to multiply all the numbers that I see in my ordered pairs by my scale factor. So like I've got to do 1 times 3 to get 3. I've got to do 2 times 3 to get 6. I've got to do 2 times 3 to get 6 again, 2 times 3 to get another 6, -1 times 3 gives me -3, and 1 times 3 gives me a +3. So again, I'm multiplying to get all of those, not adding. Let's go graph them. So over 3, up 1, 2, 3, 4, 5, 6. There's the new A. Over 6, so 1, 2, 3, 4, 5, 6, up 6, there's the new point B, and -3, +3, there's the new point C. So it's a bigger version of the triangle that I originally had, something that's not an isometry. For number 16, I'm going to have, I think, different points, so -2, 4, 8, 1, 2, 3, 4, 5, 6, 7, 8, 4, and -4, 8. So a giant triangle. And I'm this time drawing the image under a dilation of a scale factor of 1/4. So I've got a number as my scale factor that's smaller than 1, meaning this is going to be a reduction, or the shape that I end up drawing next will be smaller than the original. Same thing, I'm going to take all the points I started with, and I'm going to multiply the coordinates all by my scale factor. But this is going to be a little bit harder because like 1/4, that's a fraction. And everybody's like, oh my gosh, fractions, I'm freaking out. Let's use our handy dandy calculator maybe to help us. 1/4, if fractions are freaking you out, turn it into a decimal. So 1 divided by 4, enter button, is 0.25. So I'm going to multiply that scale factor, 0.25, times all of my numbers up here. So I've got to do -2, -2 times 0.25 gives me -0.5 or -1/2. The other ones I think I could do in my head. 4 times 0.25 or 4 times 1/4 is 1. 8 times 1/4 is 2. 4 times 1/4 is 1. -4 times 1/4 is -1, and 8 times 1/4, 2 again. And I'll just go graph those. So to the right, or sorry, to the left a half, up 1, there's D prime. 2, 1, there's E prime. And -1, 2, there's F prime. So I've got like a smaller version of the triangle. I think we're done with dilations. Back to rotating things. So the figure below is a regular pentagon with a center O. State the counterclockwise angle of rotation that maps A onto A prime. So I'm starting at A, I'm going counterclockwise, and ending up at A prime. So right there. Easiest way to do this is to figure out my central angles. So all the way around there in the middle, that's 360 degrees. But I'm dividing that 360 into 1, 2, 3, 4, 5 pieces. So each one is going to be worth 72 degrees. I'm going to go ahead and write that in. 72, 72, 72, 72, 72. If I'm starting at A, I've got to go 72, and then I've got to go another 72 in order to get over here to A prime. So 72 plus 72, or 72 times 2, gives me 144 degrees. That would be my angle of rotation. All right. Ooh, rotating in the coordinate plane. Got some original points. I've got 1, 2, -2, 4, and 2, 2. Haha, 2, 2. And I want to rotate that 90 degrees counterclockwise. I can't really show you the paper turning trick with my computer, so I'm going to have to get my answer another way. If I'm rotating 90 degrees counterclockwise, that's going to put me, or my answer, over here in quadrant 2. When we do the 90-degree rotations and the 270-degree rotations, what ends up happening is that we switch what our original points were. We switch those values. But we have to think about what quadrant we're in and what sign everything would have. Over here in the second quadrant, the x's are negative, but the y's are positive. So all my x's are negative, all my y's are positive. And then I just have to remember to switch my x and y coordinates. So instead of being at 1, 2, I've got 2 and 1, but the 2 is negative. Instead of 2, 4, I've got 4, 2, but the 4 is negative. And then, oh, the ones where it's the same coordinate, those are the best. Those are the best ones. So let's graph that. I've got -2, 2, -4, 2, and -2, 1. Looks good to me. I'll label everything though, that's important. So A, B, and C prime. This second one is exactly the same original shape, but instead of doing a 90-degree rotation, we're instead doing a, oh, I messed that up. We're doing a 180-degree rotation. with 180-degree rotations, it's like we took this and we just turned it upside down. So 180 degrees is going to put me 1, 2 quadrants. So down here in quadrant 3, where all my points are negative. So A prime is going to have 2 negative numbers. B prime is going to have 2 negative numbers. And C prime will also negative. With 180-degree rotations, though, I don't have to switch the coordinates. I just make them negative. So I'm going to leave it as 1 and 2, just opposite signs. I'm going to leave B as 2 and 4, just opposite signs, and then C, favorite one, 2, 2. And I'll graph and check it out, see if I think it looks right. So negative 2, negative 4, negative 1, negative 2. Yep, looks good. B prime, A prime, C prime. Alright, last one for the page. What is the image of the point negative 2, 5 under a 270-degree clockwise rotation about the origin? So you could arrive at your answer by applying one of the rules from the table that we filled in as part of our notes, or I might encourage you to just graph it and kind of see what's going on. So negative 2, 5, 1, 2, 3, 4, 5 is right up here, and I'm turning it 270 degrees clockwise. So clockwise with time is around this way. So this would be where 90 is, this would be where 180 is, so a 270 clockwise rotation would put me down here in quadrant 3 again. 270 degrees clockwise, though, is the same thing as 90 degrees counterclockwise. So I'm going to end up being somewhere down here, quadrant 3, where everything is negative. And a 270 or a 90 rotation, we end up switching our coordinates. So instead of the 2 first and the 5 second, it's going to be the other way. 5 first, 2 second, and since I'm in quadrant 3, everything's negative. Let's graph it out and see what we think. 1, 2, 3, 4, 5, negative 2. So, yep, looks good. Yay! Alright. We're almost done with the first part of the test review. It has to do with transformations, and then we'll move on to the stuff with angles in another video. So a composition of reflections in 2 lines. So that means into a translation. Oh, so that's saying, like, if I had an object and I flip it over a line, and then I flip it over another line, the quicker way to get from the first one to the last one is just to slide it or translate it. So if we're trying to get a translation, we've got 2 parallel lines. But the rotation comes in when you've got lines that cross each other. So intersecting. Alrighty, point O is the center of each figure, or each regular figure. What is the image of point D under a 180-degree rotation about O? This is kind of weird because we've got 2 shapes going on at once. We've got our square and our regular hexagon. The first question we're asked about has to do with point D, or has to do with the square. So let's think about maybe just the square first. If I draw in my central angles for the square, I'm dividing my 360 into 1, 2, 3, 4 pieces. So each one is 90 degrees. So if I'm taking D and I go 180, 180, I guess counterclockwise, I guess technically it doesn't matter. Then if I go to A, I would have gone 90, I've got to go all the way around to I to go the full 180. So the image, or the place where I end up, is point I. In the next question, though, we're asked about the angle of rotation for B onto H. B and H are part of the hexagon. So I'm not going to use that 90 degrees for this question. I've got to draw in and calculate another angle of rotation. So we're dealing with B trying to get to H. Let's draw in some central angles for the hexagon. So a hexagon is dividing my 360 into 1, 2, 3, 4, 5, 6 pieces. So each one is worth 60 degrees. So if I want to go from B to H, I'm going those 60 degrees and also those 60 degrees. So a grand total of 120 degrees. Last one for this problem. What is the image of J under a 120 degree counterclockwise rotation about point O? So J is where I'm starting. J is where I'm starting, and I want to go 120 degrees from point J, from point J counterclockwise. So there I would have gone 60. To get to 120, I need to go another 60. And that puts me at point G. Alrighty, so rotate the word HI shown below. Ooh, why is my pen being funny? Counterclockwise about the origin. So 270 counterclockwise. Alright, so counterclockwise is this way. So that would be 90. This would be 180. This would be 270 if I'm going counterclockwise. Alright, so I'm going to pick out maybe just a couple of points. That one at 1, 1 is pretty easy to do. If I'm rotating something that's 1, 1, it's going to end up being at 1, negative 1. Let's maybe pick another point. So this one up here is at 1, 5. So with a 270, remember that we've got to switch them, and I'm in quadrant 4 down here where the x's are positive, the y's are negative, so I want to go to 5, negative 1. So there's like the side of my h. Once I've got that, I know, oh, this is the side of my h. I'm just going to use the drawing to figure out what the rest is going to look like. The middle part of the h has 2 units. There's the other end of the high. And then I'm drawing the rest. So I just kind of needed to graph a couple points to sort of see where the word was going to start out, and then the rest of it I can finish just by kind of counting and looking. Alright, I think this is the last one for this part of the test review, and then we'll stop the video, and you can pick up on the other one if you want to see the rest of the test review. So identify the figure that is a identify if the figure is a translation, rotation, or reflection of the original figure. So if I look at at A, the triangle I is switching sides, where I'm switching orientation, almost like I'm kind of flipping over a line. So A is the reflection. B, I'm taking this guy and I'm turning him upside down. So that one's the rotation. And C looks just the same as the original, I just moved it over here. So this is the translation. Cool. So part of the test is going to be about all that stuff, and then the other part will address the problems in the rest of the test review. So if you want to see more about those, check out video number 2.